The first thing that we have to know in chapter 3 is the variations and trends in periodic table, which involve three things. That is when moving across the period from left to right, and when going down the group, and the last one will be specifically for the transition element in period 4. So we're going to divide the periodic table into three blocks. Okay, so the first one in the left would be the S block, the middle one is the D block, and the right one would be the B block. Remember that we don't deal with F element of F block in matriculation syllabus. For S block, it consists of group 1 until group 2, which is all metal. But beware guys, in P block, we do have the metals as well. I've already highlighted it in pink color. So these pink elements are metal as well, which are the aluminium, barium, and so on. For the blue elements that I've highlighted, this one is the metallite. So metallite is the mixture of metal and non-metal. So I'm going to highlight the elements that involve as non-metal. So for the rest of the elements, except the one in pink and blue color, these are non-metal elements, such as for chlorine, bromine, and group 18 elements. Okay, except for the pink and blue, these are non-metals. For the D block, they will exist as transition metal. So you're not be given this periodic table in examination. So you have to remember which are the metallites, which are the metals, and which are the non-metals. So first trend that is moving across the period from left to right. Okay, you must state this in your explanation because it can go the other way around. Okay, so from left to right, the proton number will increase. For example, when we are going from lithium to neon of the same period, which is 2, okay, the proton number increased from 3 to 10. Hence, the effective nuclear charge, in short form ZEV, will increase as well. So the attraction between nucleus and outermost electron will increase. This causes the atomic radii to decrease, okay, at this point in your note. And lastly, the ionization energy will be increased alongside with electronegativity. Hence, we're going to say that the IE is directly proportional to the electronegativity. So don't write in short form for FSPM, okay? Write in full words, electronegativity. Second, when going down the group, the number of shell will increase. So they will increase the shielding effect as well. Hence, the attraction between, you must mention nucleus and outermost electron will decrease. So atomic radii will increase. So take a look at your periodic table. So let's say we're moving down from group 1 or group 2 lithium to group 4 of potassium. So lithium would have 2 shells, while the potassium would have 4 shells, because the N is equal to 4. So hence we're going to say that the atomic radii increase, the size becoming bigger. So the IE will decrease along with the electronegativity will decrease as well. So we have come to two terms that we are not familiar with, which are the effective nuclear charge, ZEV, and the shielding effect. So when mentioning the trend across the period, you must mention the Z. For the trend down the group, you must mention about the shielding effect. So I'm going to explain both in the next pages. So the effective nuclear charge, or ZEV, is the net positive charge felt by the outermost electron. So it has the formula of Z minus S, where Z is the proton number and S is the inner electron. So inner electron is the one that is not in the valence shell. So I'm going to take, for example, sodium and argon. They are both located in period 3, means they have the same shell of 3. So for sodium, the proton number is 11. So we're going to fill in the first shell with 2 electrons and the second shell with 8 electrons and the last shell with a valence electron of 1. So the calculation for ZEV, that would be the proton number is 11 and the inner electron is the one that I've highlighted or I've drawn in red. So that would be 2, 4, 6, 8, 10. 10. So the Z would be 1, but you must write it as positive 1. Okay, so sign is included. For argon, it has the proton number of 18. So we're going to fill in the first shell with 2, the second shell with 8 electrons, and the third shell with 8 electrons as well. So now we're going to calculate the ZEV. So the proton number is 18 for argon minus the inner electron. Remember the inner electron is the green one because it is not located in the valence shell. Okay, so 18 minus 10, that would be positive 8. To summarize, when moving across the period from left to right, okay, we're going to observe that the proton number increased from 11 to 18. So Z will increase going from positive 1 to positive 8. So the attraction will increase as well. So what's going to happen to this valence shell of argon? It will be attracted towards the strong nuclear charge. So this valence shell will become closer, but still the electron or the valence electron remains. So we're going to say that the atomic radius or radii will become smaller or decrease, okay, because it has a higher Z of positive 8. Shielding effect or screening effect. We usually use the term shielding effect for manipulation. It is the attraction between nucleus and electron. So we're going to discuss shielding effect based on the trend of going down the group. As I mentioned before, when going down the group, your N increase, hence your shell will become larger or bigger, right? So I'll just draw this for example. So let's say we have Abu and Ali in the middle of the nuclear charge. So this is Ali and this is Abu. So they both are going to be attacked by a group of zombies. So we're going to see how they're going to shield themselves from the zombies. For Ali, it has N equal to 2 shell. So for each shell, I'm going to put 2 bodyguards, which is red in color. For Abu, okay, he's got 1, 2, 3, 4, 6 bodyguards to protect Abu from these zombies. So who are being shielded more from the zombies? Yes, that will be Abu. So we're just gonna imagine that when there is more bodyguards, hence the electron become more shielded. So to summarize, when going down the group, the shielding effect will increase for Abu, so the attraction will decrease because Abu is no longer being attracted to the zombies, right? So the atomic radius will increase, obviously, because the shell for Abu is larger when going down the group. In order to understand better how does the atomic radius across first row of transition elements changes, we need to understand which orbital has the higher energy. Okay, so remember your off-bound. So 4s has lower energy than 3d. So make a short note, or we can say that 3d orbital has higher energy than 4s. So we'll just be discussing the transition elements in period 4 specifically for chapter 3, which is going from scandium to zinc. So we've got 3 trends in here. That is the first one, going from the scandium to the chromium. The atomic radius will decrease. So let's look at their valence shell. So for scandium, titanium, vanadium, and chromium, the 4s is fully filled. Meanwhile, the 3d is filled with 1, 2, 3, and 5. So we got to explain that when 3d orbital is filled first instead of 4s, okay, so 3d has higher energy, so the nuclear attraction will become stronger. Together with the electron repulsion will become stronger as well. Remember, when attraction is stronger, okay, that means that your atomic radius will decrease or shrink. Okay, you just imagine it like this. Okay, so when these red electrons are being attracted towards the strong nuclear charge, so what's going to happen is that the shell will shrink. Okay, so it's reduced in size. The second one, going from manganese to nickel. So from manganese to nickel, we have this trend, okay, which is in constant value. So the valence shell would be this one. So we're going to observe what the difference between the 4s and 3d for these elements. So for manganese, we're going to fill the 3d with 5, 6, copper 7, and nickel with 8 electrons in 3d orbital. So the 4s is fully filled together with the 3d orbital. Okay, so for manganese, the 3d5, so 3d5, okay, we're gonna say that it has a half field stability, which means that the 3d orbital is going to be fully filled, okay, by extra 1 electron, that is from 5, 6, 7, and 8 electrons. So the nuclear attraction is equal to electron repulsion. So that's why the atomic radius does not have any drastic changes in here. So the atomic radius will remain constant because 4s and 3d is going to be filled at the same rate. The last one would be for copper to zinc. Okay, for copper to zinc, this is the trend. The atomic radius increase. And why is that? We're going to take a look at your valence shell. So for copper and zinc, copper has 4s1, while zinc has 4s2 electron. And the 3d is already fully filled with 10 electrons. So 4s is being filled instead of 3d. So 4s is lower energy, right? Hence, the nuclear attraction and electron repulsion will become weaker, or you're going to say decrease. Okay, so electron repulsion will become weaker as well, so the atomic radius will increase. So remember, when you are not holding something very tightly, Okay, then it will be easy for you to let it go. So the atomic radius will increase. So in short, the changes in atomic radius across the first row of transition elements happen because of the difference in how 3d and 4s orbital are being filled. Okay. So we got three trends, which is go, the atomic radius decrease, and then the atomic radius become constant and then increase finally.